Okay, so we just finished talking about making confidence intervals for proportions, and we are still continuing on with dealing with categorical variables. And so we're now going to learn the chi-squared goodness of fit test. Okay, so confidence intervals for proportions are useful if we have, I guess what we call like dichotomous categories. So if the category is, it's either this thing or it's not, kind of like a binomial situation, confidence intervals are good for that, because then we could just see the proportion in the population that have that category, okay, or that characteristic. If we have more than one category, then we might be more inclined to use what we call a goodness of fit test. Okay, so rather than just saying male or female, maybe we are dealing with a situation where we have multiple categories. So we could be dealing with like flowers, and maybe the flowers are supposed to be red, pink, and white. Okay, and so we have three categories, and we want to know, okay, are the flowers showing up with certain proportions? Okay, so we have what we call the chi-squared goodness of fit test. Okay, chi is spelled C-H-I, but it's pronounced chi. It's the Greek letter. I guess that would be most close. That looks a lot like X. The chi-squared goodness of fit test. And the idea here is we've got one categorical variable. Okay. And this categorical variable can take on either two or more categories or values, okay? Two or more values. So for example, we could have two values such as male, female, okay? Or it could be, you know, three values, and we're talking about colors of a plant. It could be red, pink, white, etc. Okay. And here we have an idea of the proportions for each of these values, okay, for each category. So we might think that in our hypothesis, we specify our belief of the proportions for each category. So maybe we might believe that for the flowers, show up with the following proportions or probabilities. might say red shows up 20% of the time, pink shows up 50%, and white shows up 25. Okay, and so you might go gather a random set of flowers, okay, and you might count how many we have. Okay, so our data is we gather flowers. Okay, so let's say we gathered 400 flowers. And these are the counts. Color and count. No, that doesn't add up to 400. Okay. I think that adds up to 400. Yes. Okay, and so we want to know, does our data contradict the proportions we have in mind? Okay. Or, we want to use the terms of the test, goodness of it. How good or how well do our proportions fit the data? Okay. How well do these proportions fit the data we observe? So it's, what is the goodness of the fit, okay? Data. Okay, so our null hypothesis is along the lines of the proportions, the specified proportions. I'm sorry, the null hypothesis, yeah, is that the population has the specified proportions. Okay. And the alternative is that at least one of the proportions is wrong. Okay. And so we're not specifying which proportion is wrong, we're just saying at least one of these proportions is wrong. Okay?
Would that indicate that the other proportions are wrong?
Yes, but it avoids saying which of the other proportions are wrong, okay? Because everything has to add up to 1, right? So let's say it's this category that's wrong, okay? The proportion of white flowers is wrong. So let's say it turns out that this number is too big. So I have to shrink this, okay? So if I'm shrinking this, then that means the other part, for it to add it to 1, has to go to either pink or red or some combination, okay? And so we don't specify that which one, where it goes in the other side. So we're just saying at least one of the proportions is wrong, okay? when you're not specifying which one is wrong and which one is big or small or whatever like that, this is, it's going to be a non-directional alternative, okay? You can have a directional alternative, and we'll talk about that situation in a moment here, okay? But so when you're just saying at least one of these proportions is wrong, it's going to be a non-directional alternative. Okay, so this is what our data looks like. This is what the proportions that we have in mind are. Do our proportions in the data, do they fit well together or not? So to carry out the test, we calculate a chi-squared statistic. Okay. So the chi-squared statistic basically shows us how different is our data from what we would expect if our proportions were true. Okay, so we have to create expected counts. Expected counts if the null hypothesis is true. Okay, so essentially all I'm going to do is take my total sample size, 400, okay, and just multiply it by my proportions. N is 400, total sample size. Okay, and multiply N by our proportions. Times 0.25, I would expect 100 red flowers. I do the same for the pink, and I would expect 200 pink flowers, and I would expect 100 white flowers. Okay, because my proportions were 0.25, 0.5, and 0.25. So these are my expected counts. And I'm going to contrast this to my observed counts, which were 92, 212, and 96. So the chi-squared value consists of the observed value minus the expected value squared over the expected. And we do this for all categories. So I'm going to do 92 minus 100 squared over 100. So this would be technically for red. And then you could go for pink. 212 minus 200 squared over 200. And for white, 96 minus 100, or 100. So I get 12 minus 2, 144. 2. I should just double check. Okay, and so when I total this up, I get 1.52. Is the process that I went through okay so far? Okay, So my chi-squared statistic is equal to 1.52. And so what do we do now? We go to our reference tables, and we're going to look up our test statistic to get the corresponding p-value. Okay, so the chi-square table has what we call degrees of freedom. Degrees of freedom for a categorical variable is the number of categories minus 1. Okay, so for the chi-square goodness of fit test, the degrees of freedom is the number of categories minus 1. So how many degrees of freedom do we have here? 2. Okay. So I have 3 colors, red, pink, and white. So I have 2 degrees of freedom. And so you use this in a very similar way as you would the t-table. And so according to this, what would my corresponding tail probability be? Over 0.2. I'm using table 9, critical values of the chi-square distribution. So I'm looking at the row 2 degrees of freedom. And the first value I see there is 3.22, and the values just get larger from there. So my chi-squared statistic of 1.52 is smaller than 3.22. So that means my corresponding tail probability is larger than 0.2. So we look it up and look up 1.52 in the table, in chi-squared table, and what we get is our tail probability is greater than 0.20. Are there any questions? Yes?
So if it was non-directional, you would just do it in half? Because that's what it says, right?
So if it were directional,
Oh, if it is directional.
you would divide the column headings by half. So again, read the top of the thing. So right now we're just talking about the tail probability and we haven't found the p-values yet. But in this case, when you have a non-directional alternative, which I said that's what we have, our tail probability is our p-value. So in this circumstance, our p-value is greater than 20%. P-value is greater than 20%. Okay, because if you read the table, it says the column headings correspond to non-directional alternatives. We have a non-directional alternative, so our tail probability is our p-value. You get what it, yes?
So if it was directional, it would be half?
If it were directional, we would divide it in half, assuming we passed our directionality check. Okay, so what does our p-value mean? What was the definition of a p-value?
Probability.
So p-value is the probability of observing our data or something more extreme if the null hypothesis were true. Okay. So our null hypothesis says that the population has the specified proportions. So if flowers truly appear red 25% of the time, pink 50% of the time, and white 25% of the time, if that was the true proportions in the population, what is the probability that I take 400 random flowers and I get something that doesn't reflect that exactly? Something like this, or something even more unusual than this. Okay? Because here we're getting more pink flowers than we expected and not as many red or white flowers. How unusual is data like this? Well, it turns out, when we go through the math, that we would get stuff like that over 20% of the time. Okay, that's what our p-value tells us. So seeing too many pink flowers, 12 more pink flowers than I might have expected, and 8 fewer red flowers and 4 fewer white flowers, turns out it's not that big of a deal in this case. Is that okay? So our p-value is greater than 20%, so let me just write that down. Definition based on the p-value, so we would say if the proportions, that is, red is equal to 0.25, pink equal to 0.5, and white equal to 0.25, are actually true, then the probability I see data like ours, or something more extreme, is over 20%. So we have no reason to reject the null hypothesis. Or we have no reason to reject these specified proportions. We have no evidence to reject the null hypothesis, sorry. We have no reason to believe these proportions are wrong. Okay. And move forward. With the chi-squared goodness of fit test, you might have a directional alternative. But the directional alternatives can only happen if you have 1 degree of freedom, or in other words, when you only have 2 categories. So you can have directional alternatives there's only 1 degree of freedom, or in other words, when there are only 2 categories. And that's because if we can say category 1 is, the null hypothesis says that category 1 has this proportion and category 2 has the other proportion, 1 minus that. The alternative could say category 1 is actually larger, which then forces that category 2 is smaller. Okay, so the null hypothesis could be something like the probability of category 1 is equal to p, which requires that the probability of category 2 is equal to 1 minus p. Right? And then the alternative could then be probability category 1 is greater than P, which forces probability category 2 to be less than 1 minus P. Because we know that if there's only 2 categories, and we have category 1 and category 2, and we know that category 2 is just going to be 1 minus P, a lot of times we will just write this as probability of category 1 is equal to P, and then the alternative, probability of category 1 is greater than P or less than P or whatever we want, okay? Because it would be redundant. It's essentially redundant to fully write out category 2 probabilities there. Okay? Whereas when we had, red, pink, and white, we had to say 25%, 50%, 25%, okay? But in these cases, when we know there's only 2 categories, this or not that, we'll do this, okay? And again, whenever you have this, you have to do a directionality check. Okay, so anytime you have a directional alternative, we have to do a directionality check. So if the alternative says that the probability of category 1 is greater than P, then your data should support that. Okay, your data should support whatever the alternative says. And if it doesn't, then there's no point in continuing on with the test. You would have no evidence to support the alternative. Okay, so let's try an example. Let's see. So this is an interesting example. And this was a real study. They wanted to know, do we as people, can we kind of influence when we die? Right? And so to study this, what they did was they looked at a bunch of old people, and they wanted to know, can they influence the time they die? And so they chose elderly Chinese women over age 75, and there's this annual Harvest Moon Festival, and they picked that because the date of the festival is not necessarily the same each year, and the elderly, like the grandmother or the matriarch of the family plays an important role in this thing. Okay? And so they wanted to see are the elderly women more likely to die after the festival than before, okay? Because if people had no influence over when they died, then they should die with equal probability before as they would after. But if somehow people could influence when they die, then they would expect more people to die after and fewer to die before. Does that kind of make sense? So that's what they studied, okay? So according to this, so they observed just I have a bunch of data here, okay? So under the null hypothesis, the probability of die after the festival is equal to 1/2. And then the alternative is that the probability that who dies after the festival to be greater than 1/2. Okay. And so they looked at 103 total deaths in the times prior and after. Okay. And this is the data that they collected. So, died before and died after. Oops. Okay, so this is what we observed. We saw 33 had died before, and 70 had died after. If the null hypothesis were true, what would we expect? Expected under the null hypothesis, a total of 103 deaths. So we would expect half to be before and half to be after. So we would expect 51.5 before and 51.5 after. It's okay that we have a decimal, because these are just expected values, not anything that we would observe. Okay, so then we would go about calculating our chi-squared statistic. What does that turn out to be? So I get 6.65 plus 6.65. Get 13.3. So I go to my chi-squared table. I have 1 degree of freedom. And I find that my tail probability is between 0.0001 and less than 0.001 at 13.3. When I do my directionality check, we want to see, is the proportion that die after the festival greater than 1/2? And we see yes, it passes the directionality check. What we observe is indeed over 1/2. Okay, so directionality check. Passes. The proportion that died after the festival is indeed greater than 1/2 in our observed data. And so that means when we calculate our p-value, we would take our tail area and divide that by 2. So we have a p-value that's between 5 in 10,000 and 5 in 100,000. So a very small p-value. So that says, if this null hypothesis were actually true, what's the probability that I would see data like this or something more extreme? It would happen, it could happen by random chance, but it happens by random chance very, very, very rarely. Between, less than 5 and 10,000 times. So rather than saying it happened by random chance, we're willing to say this is not a result of random chance, okay? we're going to reject the null hypothesis and say we do have evidence that the proportion of elderly Chinese women that died after the festival is greater than 1/2. Okay, so we have evidence to reject the null hypothesis. And we can conclude the alternative, which would suggest that to some degree, people might be able to influence their date of death. The mechanism behind that, not known, but this data would seem to indicate something is possible. Yes?
So once we have our p-value, what are we comparing it to make that conclusion? That we have evidence to reject the null?
I did not specify an alpha, but this is a very small p-value.
Yeah.
Even if I said alpha was 1%, and generally you don't see alpha as much smaller than 1%. So even if I were to say alpha is 1%, this is smaller than that. So I did not specify an alpha, but it should be clear that this p-value is quite small. Small enough to reject the null. So that is the goodness of fit test, chapter 9. Are we feeling okay with this? If you guys are willing to stay with me, we're going to move into chapter 10, where we extend the chi-squared test to see if there is a relationship between two categorical variables. Okay? So this would be the chi-squared test for independence. And again, we have categorical variables, but now we are using the chi-squared test to see if there is a relationship between two categorical variables. Chi-squared test for independence. Okay. And so the chi-squared test for independence depends on this one rule from probability. Okay? And that goes, if events A and B are independent, okay, you guys remember this? The probability of A and B is equal to the probability of A times the probability of B. Okay. So we're going to use this as our guiding principle behind the chi-squared test for independence. Okay, so let's just do a silly example. Okay, and so we will say variable 1 will be gender, or the sex of a person, male or female, and variable 2 we will say long hair or short hair. Now, technically, the length of hair could be a numeric variable, okay? And then we can do, you know, is there a difference between the mean length of hair for males and females? But let's say we just turned it into a categorical variable. And we say, somebody has long hair or they have short hair. And I understand that this is fraught with problems in terms of what is long hair and what's short hair, but let's just say, you know, you self-classify, you have to answer a survey. Do you have long hair or short hair? You just have to pick one. Are you male or female? You have to pick one. Okay. Alright, so let's say, well, how should we display our data? Okay, the data that we collected, when you have two categorical variables, what do we use? Tree. Two-way table. Okay, so we're going to have male, female, and we'll say long hair and short hair. Alright, let's just, we'll make our numbers easy to deal with. So we'll say we surveyed 1,000 people, and I guess to make this more interesting, let's say we went to a place where there was more females than males. Okay, so we had 600 females, 400 males. And we will say 40, 360, and 480, and that gives me 120 here. So we have a total of 520 and 480. So this is the observed data. Okay. And this is, I picked this silly example because we kind of already know the answer to the question. Is there a relationship between gender and the length of hair, whether someone has short hair or long hair? And we know the answer is yes. Women tend to have longer hair than men in general, okay, generally speaking. So that's our data that we gathered. Okay. So this is a test to see if there is a relationship between two categorical variables. The null hypothesis in these tests is that no, there is no relationship. And the alternative is that there is some kind of relationship. The null hypothesis would be that there is no relationship, or in other words, the two variables are independent. And so, saying that the two variables are independent, we can write this symbolically in all sorts of ways. Okay, so with words, we can just say that two variables are independent, or that gender and length of hair are independent or are not related, things like that. Okay, so in words, we can say gender is independent of hair length. We want to use symbols. We could say the probability that someone has long hair, given that this person is male, would be the same as the probability that someone has long hair, given that this person is female. Or any variation of this also. This is one possible way to express it. And then the alternative is that not independent, basically. So in our calculations, we want to know how far does our data deviate from what we might expect. So what would we expect if hair length and gender are independent? So when we look at our data, we see a total of 520 people have long hair. So if I pick someone at random, what's the probability that this person has long hair? We would write the probability of long hair is equal